Okay, so to recap, we will be going over today about Chapter 7 material, and it's going to be over Lewis structure as well as charges and ionic and covalent bonds and what the difference between those two are. So yeah, let's get started on the first question. It's question 12. So let's do this. Okay. So the question is, what information can you use to predict whether a bond between two atoms is covalent or ionic? So the difference between these two is quite simple. So a covalent bond is going to be between a nonmetal and a metal. And also the ionization energies between the atoms in the covalent bond is going to be very, very similar or the exact same. So they're going to have identical / very similar ionization energies. And so the difference between the covalent bond and the ionic bond is going to be that they're going to have, oh, sorry, in the last question, covalent bond, my bad, both are going to be nonmetals. And so an ionic bond is going to be between a nonmetal and a metal. Sorry about that. Yeah, so that's the two differences between the covalent and the ionic. Yeah, paying attention to the ionization energies as well as, if it's a metal or a nonmetal. And later on, we will be talking about the electronegativities. So if you've gone over electronegativities in your own class, the differences between the two atoms, their range or their value of that difference is going to tell you whether or not it's going to be a polar or a nonpolar covalent bond, and if it's going to be ionic as well. So if it's, I believe it's 1.8 or up to 4, the difference of the two atoms, it's going to be a ionic bond, and if it's below 1.8, it's going to be covalent. But the differences between covalent is there's polar and nonpolar, and we will get into what the two differences, what is the difference between those two. And a polar covalent bond will have a difference of electronegativity of 0.4 to 1.8, and then below 0.4 is going to be nonpolar covalent. But we will get into that with more specifics later. Okay, so let's move on to the next question. Awesome. Okay. Let's read this out. Okay, so this is predict which of the following compounds are ionic and which are covalent based on the location of their constituent atoms in the periodic table. Okay, so the first one is chlorine to carbon and oxygen. So chlorine is a nonmetal, and carbon is a nonmetal, and also oxygen. So all of these are going to be nonmetals, and because they are all nonmetals, this is going to be a covalent bond. So it's pretty simple to tell. And if you don't know that right off the bat, you're like, oh, chlorine, is this a metal or a nonmetal? You can always go to a periodic table. And so these are going to be your metals right here. So the transition metals in the group in the center, and then the alkali and alkaline metals, and also these down here, but you're rarely going to be using these really, really super big atoms down here. And then these are all going to be nonmetals except for your semi-metals, but don't worry about that for now. Yeah, your semi-metals are going to be in this area. I forgot which one specifically. But yeah, those are going to be basically your metals versus your nonmetals, and aluminum is obviously going to be a metal as well. So, since our first one is chlorine, carbon, and oxygen, it's covalent, and for 13b, this is manganese oxygen. So manganese is a metal, it's a transition metal, and oxygen is a nonmetal. And so because there's a metal and a nonmetal, this is going to be the ionic bond. Awesome. So let's move on to 13C. This is nitrogen and chlorine. Nitrogen is a nonmetal. Chlorine, as we already established, is also a nonmetal. So this is going to be a covalent bond. Okay, and the next one is cobalt and bromine. And so since cobalt is a transition metal as well, and bromine is a nonmetal, this is also, or not also, this is going to be an ionic bond. And the last one here is K2S. This is potassium and sulfur. So it's potassium sulfide. And since potassium is an alkali metal, it has a +1 charge, so it's on the very left on the periodic table. This is going to be an ionic bond because of the ionic, or because of the metal and the nonmetal forming a bond. So they're going to give and take electrons. And like covalent bond, they share electrons. Alright, so let's move on to question 14. So I touched on this a little bit earlier, but now we get to address it specifically. It says, explain the difference between a nonpolar covalent bond and a polar covalent bond, as well as an ionic bond. Okay, so an ionic bond, I just said this, but we're saying it again. An ionic bond is the transfer of electrons, so one atom is going to be giving and the other one is going to be taking. And the differences of their electronegativities is going to be 1.8 to 4. And so that's what an ionic bond is specifically. So let's write that down. Write it down in red. So ionic bond is going to be transfer of electrons, giving and taking, and their difference, so that's delta, that's what that symbol is, the difference in their electronegativities is going to be, is going to be between 1.8 and 4. And so that's what an ionic bond is. And so for covalent bond, but for a nonpolar, covalent. So nonpolar covalent, so covalent bonding is going to be the sharing of electrons. And so the difference between nonpolar and polar, so let's just first write down covalent bonding. So covalent bonding is the sharing of electrons. So these two atoms are going to be, it's going to be moving around, but it's going to be sharing and distributed. Sorry about that. It's going to be distributed between both of the atoms, whereas with ionic bonding, we're going to give the electron to potassium and chlorine, right? The chlorine is going to accept the electron from potassium because they have +1 and -1 charge. But with covalent bonding, it's different because it's kind of it's not transferred, but it's circled around those two atoms, and they're going to hold on to it evenly with a nonpolar covalent bond. So that's where the difference between nonpolar and polar comes up. So a nonpolar covalent bond has to do with a even distribution with the charges, as well as the geometry of the molecule if there's more than two atoms. So if there's more than two atoms and you have something that looks like this, you have one atom here, and then it's evenly distributed with three different atoms connected to it. It's all evenly distributed, therefore not one place is going to have more of a charge than anywhere else because of that distribution. So that would be a nonpolar covalent bond because of the even distribution of charge, as well as their difference in electronegativities is going to be between 0 and 0.4. So that's going to be their electronegativity difference. Excuse me. And so for a polar covalent bond, there is going to be an uneven distribution of charge. And one side is going to be more positive and one side is going to be more negative. So a molecule that we all know and love, water, it's a very polar relationship. It has hydrogen bonding because of its polarity. So the oxygen is more negative than the hydrogen because the hydrogen is positive, and because there is a +1 charge on the hydrogen and the oxygen has a -2, because of that charge difference, it's going to be more negative on the oxygen side than the hydrogen, and that is very good because we need water to be polar the way it behaves. It's very important that it is polar. So that is the difference between nonpolar and polar. It just has to do with the distribution of the charge and also the geometry and making sure everything is balanced. So let's write that down too. And so the difference in the electronegativity as well is going to be, between 0.4 and 1.8. So that is their electronegativity difference. So let's move on to the next question. Hopefully that makes more sense about what those three types are. Okay, so question 15 states, from its position in the periodic table, determine which atom in each pair is more electronegative. Awesome. Okay, so let's look at the periodic table. So before we go to it, let's see what we're looking for. We have 15A and it says bromine or chlorine. So let's look at that. So bromine is going to be right here and chlorine is going to be right here. And so when we're looking at electronegativity trends on the periodic table, it's going to be generally up and to the right is going to increase in electronegativity. So it's going to be moving in a direction such as this. So up and to the right, and because the chlorine is more, it's a row above the bromine, it has a higher electronegativity. Because it is smaller than bromine. It has the same exact charge, and so since it has the same charge, but it's just one row up, the one row up, the chlorine is going to be higher. When you have a smaller atom, it's going to want to hold on to its electrons, and that is what electronegativity is, how much it wants to attract an electron. So same thing with ionization energy. Ionization energy, how much it wants to keep the electrons. Electronegativity, how much it wants to attract an electron. So chlorine, because it's so small or smaller than bromine, it's going to be able to attract electrons more easily because of it has a higher attraction or higher amount of attraction for electrons. Yeah, so that is the answer for that question. So the answer is going to be chlorine. Alright, so the next one, 15D, phosphorus or sulfur. So let's look at where that is on the table. So we have phosphorus, we have phosphorus, and we have sulfur. And the same thing here, up and to the right is going to increase in electronegativity. So sulfur is going to have a higher electronegativity because it has a higher charge. It it's closer to being a complete electron, so it's going to increase in the amount of want it has to get more electrons because it's so close to being, having 8 valence electrons, being complete in its shell in that area. So because it has that, desire, it's so close to the end, the sulfur is going to have a higher electronegativity than phosphorus. So that is the answer for 15D. So it's going to be sulfur. And the last one in this question is nitrogen or potassium. Okay, so let's look at these two. So nitrogen is right here, and potassium is right here. And so right off the bat, we know nitrogen is way up there to the right. I believe it's 2 rows up, and its charge is 1, 2, 3, 4. So it's 1, 2, 3, 4. It's 4 charges to the right. So it's going to have a higher electronegativity because it wants to attract electrons a lot more than the potassium. If anything, the potassium wants to lose an electron. It doesn't want to gain an electron at this point because the potassium is a +1 charge. And so for that reason, it's going to the opposite. The potassium, it wants to take an electron from something else. So, but even if it wants to take an electron, the nitrogen is going to want an electron even more because it's way far up to the right. Yeah, so that is the answer to that question. So nitrogen is the answer. Okay, so this question says, question 19, which atoms can bond to sulfur so as to produce a positive partial charge on the sulfur atom? Okay, so we know right off the bat, or you may not know, but we can read into this question a little bit more. So it says produce a positive partial charge. So what it's really saying here is it's going to covalently bond, and it's going to be polar because it's going to have a partially positive side on one end. So because of that fact, we know, we talked about it earlier, that the difference in electronegativities for a polar covalent bond is going to be between 0.4 and 1.8. And so since it has to be between 0.4 and 1.8, we can look at what we need to have for the electronegativity to get to that difference. So I'll show you what that makes sense, or what that means. So sulfur, first of all, is going to be right here. This is our chart for our electronegativities. And it has a electronegativity of 2.5. So what needs to happen is we need electronegativity that we're finding minus 2.5, so this is the difference in electronegativities, has to be either 0.4 or it has to be 1.8. And I like to write equations for this because then you can figure out what we need for the electronegativity based on this range. So the answer to solve for x in both of these cases, adding 2.5 and 0.4 together, it's 2.9 here, and then 2.5 plus 1.8 to solve for x here, and we'll just write x1, x2. 2.5 plus 1.8, it's going to be 4.3, but the highest electronegativity value on this chart is 4. Fluorine, it has the highest, so that's the top count. It's between 0 and 4 for the electronegativity powers or values. So that is the highest we can get. So we're looking for electronegativity values between 2.9 and 4. And so when we look at the periodic table here, we can see only 4 atoms have that value. So boron has 2. So it's not between 2.9 and 4. So that is not one of them. Carbon is 2.5. Not there yet. Nitrogen is 3.0. So nitrogen is one of the atoms that can bond with sulfur to create a partial charge, because just as we established the range, so the X value has to be between 2.9 and 4. Nitrogen has an electronegativity of 3. Sulfur has 2.5. 3 minus 2.5 is 0.5, and 0.5 is between this range. And this range means that it's going to be a polar covalent bond. So that's how that works. You figure out your range, and then you look for the electronegativities that are in between that range. So nitrogen is one of them. Oxygen is 3.5, and that is between our range. So oxygen is one of those. Fluorine is 4, also within our range. And chlorine is 3, so that's also within our range. And as you can see, all of the other values are not between the 2.9 and 4 range that we just talked about. So everything else is below that, and so that means it might be a ionic or a nonpolar covalent bond. And specifically in this question, it was asking for a positive or a partial positive charge, and so that's a polar covalent bond. So these are the only 4 atoms that can satisfy that bond with sulfur. Okay, let's move on to the next question. Awesome. This is question 21. It says identify the more polar bond in each of the following pairs of bonds. Okay, so this says it is going to be HF or HCl. And looking at our periodic table, zoom in. So we have HCl or HF. So the differences between these two molecules is if the hydrogen is bonded with fluorine or if it's bonded with chlorine. And so looking at where this is located, fluorine is a row above chlorine and it has the same charge. So we know that the electronegativity of fluorine is much higher than chlorine. That fluorine is actually the highest electronegativity of all of these atoms, so we know that the HF is going to have a stronger polar bond because fluorine has an electronegativity that is higher than the chlorine. So the difference is going to be higher, meaning it's going to be more ionic for the fluorine. Okay, so that is the answer here. And the next question is PCl or SCl. So the difference between here is if the chlorine is bonded with sulfur or with phosphorus. So let's look at where the phosphorus is on here. So phosphorus is, where is it? Phosphorus is right here and sulfur is right here. And so because sulfur is more up to the right, then phosphorus, it's going to have a higher electronegativity. So that means it's going to have a stronger ionic bond. And so the answer here is going to be SCl. Or sorry, let's look at that again. I believe it's going to be Let's go over this again. If we go to the electronegativities, I wrote down a different answer than I'm thinking now. So let's look at what the actual values between them would be. So we have PCl and SCl. So PCl and SCl. So the differences between Cl, so chlorine, and sulfur is going to be 0.5. And so the difference of chlorine and phosphorus is going to be 0.9. So because the difference between them is going to be higher because chlorine is more electronegativity or electronegative. That is why the PCl is going to be more ionic because the difference is greater. Because it's actually lower in electronegativity. The last question, we did select the right one, even if we selected the one that was higher in electronegativity, but that's because the difference still is larger than the other one. So the difference of electronegativity values of HF versus HCl is higher. Same with PCl and SCl. PCl has a greater difference, and it's between the ionic bond. Awesome. So sorry, not ionic, covalent. Sorry about that. Yeah, so let's go on to 21G. So 21G, say it's CN and NN, so it's going to be carbon and nitrogen, or nitrogen with itself. And so nitrogen with itself is going just to be 0. So the electronegativity, nitrogen minus nitrogen, 3 minus 3 is 0. So it's going to be nonpolar, and we're looking for polarity in these bonds. And so carbon and nitrogen, the differences between those two is going to be 0.5. And so because it's 0.5, it's going to be a polar covalent bond. Sorry if I tripped you up. I meant to say that these are not ionic, if I mentioned that previously. These are all polar bonds, polar covalent bonds, just to clarify. Awesome. So let's move on to the next question. And so now we will be focusing on Lewis structures, and we will start off with writing down how these ions look. Okay, so we have a Lewis structure that we are going to draw for, I believe this is As3 minus, and where is that? That's arsenic. So arsenic 3 minus is our first ion that we are writing this Lewis structure for. So arsenic just itself is on the 5th column, or the 5th over on the periodic table. So it's going to have 5 valence electrons. 5 valence electrons, but because this is an ion, it gained 3 electrons because now it has a 3 minus charge. It gained 3 electrons. So adding up how many valence electrons it would now have with the gain of electrons, because it has a charge on it, it's going to have 8 valence electrons. And so with all of these Lewis structures that we are going to be drawing or writing, you always need to write down, it really does help, how many valence electrons that you're starting with, and later on we'll have more than one atom, and so writing down what each of the atoms have and then combining them, and then figuring out your calculations by writing it out really can save time and go back for checking of errors and things like that. So yeah, we always want to start out with what we have for the valence electrons, and then look at the charge for the ion, and then accommodate that for the total amount valence electrons in the end. And so now for arsenic 3 minus, that ion, we have 8 valence electrons. So now we know how many electron dots to write for the Lewis structure. So for a Lewis structure, you start out with the atom in the center. And so since we have 8 valence electrons here, we can start by putting these dots here. And so since this has 8, we can put 2 on each of the 4 sides because it is complete. And since it is an ion, this is the proper way of writing this out, is putting the charge outside of the brackets. And so that is how we write the Lewis structure for arsenic 3 minus. So let's move down to gallium, I believe. So gallium, on the periodic table, let's look at where that is. So gallium is right here, and it is the 3rd row So it has 3 valence electrons. So let's write that down as Ga has 3 valence electrons. And so since this is a 3 plus charge, we're losing 3 electrons. So we minus 3 valence electrons, or minus 3 electrons. And so since 3 minus 3 is 0, the actual Lewis structure for gallium doesn't technically exist because it's just gallium. It's just gallium 3 plus because there's no valence electrons. And so we don't need to write down a Lewis structure because of it. And so just to recap, the difference between the arsenic and the gallium, even because 5 plus 3 for the arsenic is 8 valence electrons, we do count that as a Lewis structure because it has 8 valence electrons. And so with gallium, 3 minus 3, yes, it's 0, so you might think, oh, it's 0, so it has a full valence electrons. Actually, no, because it lost its 3 valence electrons that it had, so now it has none. So that's the difference between those two. When I was learning this a while ago, I was a little tripped up by why this one is 0 and not 8. So that's the reason. So it's losing the valence electrons that it has, versus arsenic, it's gaining more electrons, so 5 plus 3, to actually have valence electrons. Awesome. So let's move down to nitrogen 3 minus. And so nitrogen has a valence electron amount of 5 valence electrons, and this is a 3 minus, so it adds 3 more electrons to it. So this will be 8 valence electrons, just as the arsenic 3 minus, 3 minus ion had. So it'll look very similar with its Lewis structure. We're going to put the nitrogen in the center, and it has 8 valence electrons, so it's going to be complete with 2 on each of the sides, like so, and brackets because it's an ion, and we need to put the 3 minus at the top right. So those are the electrons, or the Lewis structures for those ions. Let's move on to 25, and now we are working with ionic compounds. And then after that, I believe we are going to do 2 more questions working with Lewis structures. So we're going to work on more complicated ones now. Okay, so this one is asking, write the Lewis structure of the ions in each of the following ionic compounds and the Lewis symbols of the atom from which they are formed. Okay, so we have magnesium and sulfur for our first one here. And so magnesium has 2 valence electrons. And sulfur has, I believe it's 6 valence electrons. And so we know it's going to be complete in this compound because it's an ionic bond. So the 2 valence electrons that the magnesium has, these atoms, they all want to be complete in their valence shell. So they want 8 valence electrons because that's a complete amount. So the 2 valence electrons that the magnesium has will give them to the sulfur to have them have 8 valence electrons because 6 plus 2 is 8. So that is what is going to be happening with this. So let's write this down. So the magnesium, since it has 2, this is what it looks like before, has 2 valence electrons. And the sulfur has 6. And so just as long as you distribute the amount of electrons on the symbol, that's good. Like if you are just starting out, you're like, okay, this sulfur has 6. Let's do 1, 2, 3, 4. Now each side has 1 dot, and then you add 2 more wherever you'd like. Usually it's better to balance it, and so that's why you want it to be as evenly distributed on your Lewis structure. Okay, so this is the magnesium and the sulfur, and so what it'll look like afterwards is the magnesium will give them to sulfur. And so it'll be magnesium 2 plus. And since it lost its 2 electrons, it does not have a Lewis structure. And then the sulfur, it'll gain 2 electrons, so it'll have a complete 8 valence electron shell, and it'll have a charge of 2 minus. And so that's what that looks like. So just as we covered in the last problem, gallium, it had 3 valence electrons and it had a charge of 3 plus, so it lost 3 electrons, so it doesn't have a Lewis structure anymore. Just as the magnesium doesn't have a Lewis structure because it lost its only 2 electrons, valence electrons that it had. So that's what it looks like. Let's move on to the next question. We have potassium oxide. And so potassium has a charge of 1 plus 1, and there's 2 of them, so we can write down 2 of the potassium. And oxygen has a valence electron amount of 6. So let's write that down, write that out. So we have 1, 2, 3, 4, and then let's put that right here, 5 and 6. And so since the potassium has 2 right here that the oxygen wants, it will give them to the oxygen, so it'll lose that in its ionic bond. And so the potassium, there'll be 2 of them, K2 plus, or rather there's going to be 2 potassium ions, and the oxygen will have 2 to gain, so it'll have a complete 8 valence electrons. So let's write that down. So 2, 4, 6, 8. And since it just gained 2 electrons, it's going to have a charge of 2 minus. And just as we talked about before, since the potassium lost its 2 electrons, it does not have a Lewis structure anymore because it doesn't have any valence electrons, because it gave them to oxygen. Awesome, so that is the answers for 25A and D. Let's move on to question 28. Okay, so this is where we need to start counting the valence electrons for all of these atoms in these structures or in these compounds, because then we have to figure out how many electrons how many valence electrons there will be, and then figure out how many bonds, because some will have single or double or even triple bonds. And so we need to account for that in our calculations for keeping track of where the electrons are going. And so before we get started into these 4 questions here, or 4 structures, it's important to note for a single bond, there will be, and these are all, just to clarify, these are all covalently bonded, so they're all going to be sharing these electrons. So in the previous question we went over ionic bonding, which is giving and taking of electrons. These are going to be sharing of electrons. So it's going to be a little bit different because they're going to have, like I said, single, double, or maybe triple bonds. So single bonds, they share 2 electrons. Double bonds share 4 electrons. So let's write that down. Single bonds are 2 electrons. Double is 4, and triple is 6. So let's just keep that in note for now, and let's move on to these structures. Okay, so we have 2 hydrogens here, and each of the hydrogens have 1 valence electron. It's plus 1. It's on the very left of the periodic table, and so each H will have 1 electron. And so there's no charge on this, so the total, so adding up these 2, we will have 2 valence electrons, and since we have 2 atoms here, and it has 2 valence electrons that it's going to be sharing, we can classify this as a single bond. If we didn't jump already to that answer right there, we know that it can look like this beforehand. So it has 2 valence electrons, and then minus a single bond, so let's just say SB for single bond, now has 0. So for our structure in the end, it'll have one single bond, and we won't write down any other electrons because the single bond is accounting for those electrons for those two. So that is the answer right there. And I'm just circling the answer. That's not the Lewis structure. Actually, we can just do brackets. That might be better. So that is the answer for the dihydrogen, the H2. Okay, so let's move on to 28b. We have hydrogen and bromine. So hydrogen, just as we went over, has one valence electron, and bromine has 7 because it's, I believe, yeah, it's 7 rows down, or 7 columns. So it'll have 7 valence electrons, and so this does not have a charge on this compound, so there's no electrons that we're taking or giving away, or taking or giving it. So the total of these will have 8 valence electrons. So let's write down these two right here. So that we have H and Br. And so right now we have 8 electrons, and we can take care of one of those right now because we need to connect these two somehow. So we are going to add or take away a single bond from this. So we will have 6 valence electrons in result. So we will account for a single bond as well as 6 valence electrons. Let's move this over here. So this is our single bond, and we have 6 valence electrons left over, so now we need to distribute that. So the bromine, because it had the 7 valence electrons in the beginning, we will be putting them over there. And because hydrogen only has 2, because it has, an electron and a proton, it can only carry a single bond. It can't carry any more valence electrons because hydrogen doesn't have that capability. The bromine does, however, so we'll put all of those 6 valence electrons left over on the bromine. So we can see here that the bromine, 2, 4, 6, 8. So the bromine is complete here. It's nice and happy because it has those 8 valence electrons, and it's sharing the 2 with hydrogen. Okay, let's move on to the next one. And we have nitrogen oxide. And so nitrogen has 5 valence electrons, and oxygen has 6 valence electrons. Yep. And because there is a charge on here, we are going to add another electron. So plus 1 more electron. And so the total between all of these will be 5 plus 6 plus 1, and that is 12 electrons total that this compound is sharing. So let's write down these 2 atoms. So we have nitrogen, oxygen here, and because the nitrogen had 5 to begin with, let's just write this down: 4, 2, 4, and then 5 right here, and the oxygen had 6. 2, 4, 6. And because there's 1 more electron, we can put one right here. Let's actually move these right here. So that's the 6 valence electrons that the oxygen started with, and this is the 5 total that the nitrogen started with. And then since it's an ion, let's add 1 more electron right here. And so as we can see before, completing what this looks like, these 2 electrons can move to, not move, but they can create a single bond. So on our total here, let's minus 1 single bond, and so that'll be 2. So 12 minus 2 is 10 electrons. And so this will now have a bond like so. And so since this can carry more, actually let's see if that's correct, in 2, 4, 6, I believe the oxygen has a little bit too much right now. That's more like it. Okay, 2, 4, 6, and that's sharing 1, 2, 4. Awesome. Okay, so that's what that looks like. So it's sharing that single bond, but right now it can carry more bonds. So the whole point is that we want to simplify this down as much as possible. So it's carrying more of the single, double, triple bonds than valence electrons, and because this is capable of carrying more bonds, we're going to minus another one. And so this will be 8 electrons in valence electrons as a result. So now this is going to have a double bond, and so now we will get rid of, let's move this one up there. Now we will get rid of this electron right here. So those two. So because the calculations that we did, we have 2 single bonds or 1 double bond. So we'll have 1 double bond, and then we'll have 8 valence electrons added to our Lewis structure. So we have the nitrogen, we have the oxygen, we have the double bond here, and we have 2, 4, 6, 8 valence electrons. So this is satisfied with our calculations, and don't forget the charge outside of the brackets since this is NO minus. Awesome, so let's move on to the next one. So this is carbon and nitrogen. So carbon has 4 valence electrons and nitrogen has 5 valence electrons. And so since there's a charge on this, there is a gain of an electron. So we're going to plus 1 electron and then add up all these together. So 4 plus 5 plus 1 is going to be a total of 10 valence electrons total that this compound is sharing. And so since this is between carbon and nitrogen, there is going to be a good amount of bonding just from understanding, like just from looking at this. There's 10 valence electrons that we're working with here. There's only 2 atoms, so let's see if we can try to get a triple bond out of this one. So let's minus a triple bond, so TB, and a triple bond, like we talked about before, is just sharing of 6 electrons. And so 10 minus 6 is 4 electrons. So if we draw the triple bond in the center, now we have 4 more valence electrons to distribute, and we can put 2 on each side to evenly balance this. And that is the answer for this one. And so whenever you're working with these compounds and you're like, okay, is this a double, is this a triple, is this a single bond, you can always work back and think like, okay, let's just say this was, instead of 10, it was like 5 valence electrons, and then you wanted to do a triple bond and 5 minus 6. Well, that doesn't work. You know, you can't have a negative amount of electrons when you're doing these calculations. So you can always take a step back and you're like, okay, it's not a triple bond, maybe it's a double bond. So 5 minus 4 is 1. So it works out. So if you did too many bonds, you can always work back and start your calculations over, because it's pretty, it's just adding and subtracting. So there's no shame in, doing it over again. And don't forget that there is a minus at the top right as well. Awesome. Let's move on to question 30. This is going to be our last question of the day until next week. And we are going to do the Lewis structures of these 2 different compounds. And so now we're not just working with 2 different atoms anymore. We're working with, or not just 2 different atoms, we're working with, for the first question, 30A, 4 atoms, since we have 1 chlorine and 1 chlorine and 3 fluorine. And for 30D, we have 6 fluorine and 1 phosphorus. So these 2 are a little bit different than the others that we just worked on. So let's get through it. Okay. So we have chlorine for the first one, and chlorine has 7 valence electrons, and fluorine has, and since we have 3 of them, you do 3 times, and fluorine has 7 valence electrons. And so that equals 21 total for those 3 fluorines. So we have 7 plus 21, and so 7 plus 21 equals 28 electrons. Excuse me. And so since we have 28 valence electrons to work with, there's going to be some bonding that we can use with those valence electrons. So let's write this down. Right there. Okay, so we have chlorine, fluorine, and whenever you're writing down these Lewis structures for more than 2 atoms that you have to draw, try to balance the amount of circling atoms that you have from the center. And I didn't go over this specifically, but usually the first atom written is going to be the center atom when you only have 2 different ones. So the chlorine is going to be at the center, and the 3F is going to be surrounding the chlorine. And so since we have 28 valence electrons to work with here, there's 3 possible connections. And so let's just first start out with taking away 3 single bonds. So let's see what that'll look like. So minus 3 SBs, and SB stands for, a single bond. It can share 2 electrons. So 3, actually let's write this down specifically, 3 times 2 is 6, so 28 minus 6 is 22 electrons. So let's write down those single bonds that we just calculated for. And now we have 22 remaining. And if we look at these three fluorines here, 22 divided by 3-ish is going to be around 7. And since, 7 and some change, and since chlorine is actually, I forgot to mention this rule, that chlorine, when you have a row 3 atom, it can actually carry more than 8 valence electrons. So when you're distributing these valence electrons, keep that in mind, that the chlorine actually can hold more than that. So let's distribute these 22, and I'll show you what that looks like. So we have 22. So let's put, if we put 6 valence electrons on each of these fluorine, let's minus 6 times 3, minus 6 times 3, so that's 18. So 22 minus 18 is going to be, what is that, 4? So we're going to have 4 valence electrons after we distribute 6 valence electrons to each of these fluorine. So we have 6, 6, 6. Awesome. And since these fluorine, there's 6 valence electrons, and then there's a bond that it shares, which is 2. All of these fluorines are complete right now because they're sharing 8 valence electrons. And just as we just did, we now have 4 left over to distribute. And so, like I said before, the chlorine can carry more than 8. So we will put the remaining 2, or remaining 4, on the chlorine. And right now it's sharing 2, 4, 6, 8, 10. So it is carrying 8 valence electrons. And usually it can only carry 8 with other atoms. But yeah, that is what that one looks like. So that is the Lewis structure for that problem. Okay, let's move on to the next one. And also let me know if, any of this is confusing. I can slow down in any of the areas that you would like me to. Just let me know in the chat. Okay, let's move on to this one. This is phosphorus, and it has 6 fluorines, and it has a minus charge. So let's write down how many valence electrons we're working with here. So we have phosphorus, and phosphorus has, I believe, let's look at the periodic table because I'm not too sure off of the top of my head. So phosphorus is right here. So it's 1, 2, 3, 4, 5 columns down. So it's going to have 5 valence electrons. Yep, so it has 5 valence electrons, and fluorine has 7 valence electrons, but we're working with 6. So we have 6 times the 7, and so now we have 42 valence electrons. And since we have a charge here as well, because this is PF6 minus, so we have 1 extra electron, so plus 1 electron. And so adding up all of these, the 5, 42, and the 1, we will have 48 valence electrons to work with. And so let's start by thinking about how many bonds we will be working with this ion. So we're going to have phosphorus in the middle because it's the first one written. It's oftentimes written like that. And we have 6 fluorine. And I'm going to write 3 like this and then mirror it below so it's nice and distributed. And so as we can already see here, this phosphorus has to connect to each one of these fluorine, but we have 6 fluorine here, and if it shares 2 electrons in between each one, 6 times 2 is going to be 12. And so just as the chlorine in the last problem was able to carry more than 8 valence electrons, or not carry, share, the phosphorus, it's also in the third row, so it can also share more than 8 valence electrons, so it can also do that. So in this case, it's going to be sharing 12 valence electrons instead of 8. So let's first write that down. Since we have 1, 2, 3, 4, 5, 6, so let's minus that from how many valence electrons. So we have minus 6 times 2, since it's a single bond. And so 6 times 2 is 12. And so 48 minus 12 is 36 valence electrons. So now we will have 36 valence electrons to work with. And since we have 6 fluorine, if we divide by 6 fluorine, we will have 6 valence electrons per fluorine. So let's distribute all of those. So we have 6 on each. And so before putting those down, just to double check, if we added 6 fluorine to, or 6 valence electrons to each fluorine here, there's going to be 2, 4, 6, 8. So the fluorine is going to be satisfied because it has 8 valence electrons. And so let's write down all of those. So 2, 4, 6, so we have 6 here, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30, and 32, 34, and 36. So that is going to be the 6 valence electrons that we used up. So we had 36. Let's just erase all this math. So 36, and we used up 36 valence electrons, and now we are done because we distributed all of those. So that is what this one looks like, or this ion. And this has a minus charge. And so let's move this up here, not to confuse it. So that has a minus charge right there, just in case you didn't see it. Yep, and that is how you write down those Lewis structures. So that is actually all we have for today. We went a little bit over time today, actually. But yeah, let me know if you want to go over any of these specifics, but that is what all of these look like. As you can see, it's really make your calculations and making sure where to follow everything and to keep track of everything where you're writing down these bonds. Oh, we have a comment. Thank you for streaming this content. I'm not studying chem, but I'm glad you are sharing this content. See you around. Yeah, of course. I'm glad that, maybe it was helpful. Thank you for listening. Of course, yeah, I'm streaming each week on Fridays if you're interested in keeping up with learning this kind of material in chemistry. But yeah, so this is all of the material I have for today. Let me know if you have any more questions at all, and I will see you guys next week, if not. So have a good weekend and have fun studying.